So in the last class, we have seen these general cases for resonance, right? So we have seen these 13 cases, and then we have, generalized it to these two structures, right? So mainly it is A double bond B, then C, and on C there can be either there can be positive negative charge or a free electron or a lone pair or a double bond or a triple bond. So these are the different cases. Now let's see how this results in transfer of electrons, or basically the electron flow directions. So that's our next thing, that is direction of electron flow. So how does that happen? So I asked you to write for all the 13. So whatever you have written, you can verify from the cases and the diagrams which I am going to show here. So the first one was this case, A double bond B, single bond C, and on C there was a positive charge. So this is, or this positive charge is the point of, or is the site of electron deficiency. Double bond means there are p orbital electrons, right? Double bond means there is a pp pi bond. So that pi bond electrons will be used here. So how does this happens? From this position, it will be given to this. So what we'll have next structure is A single bond B and double bond C. Now because from A and B, if you see A and B were sharing 2 electrons, those 2 electrons are now being shared by B and C. So no change has happened with, or there was no change in share of electron for B, but A has lost electron. So that's why there will be a positive charge there. Okay, next case. Next case is when we have a C, on C there is a negative charge. So now negative charge means that is the site of, or that is the high electron density is available there. So electron should move from there to the next available site to form a pi bond. And obviously now this B may not be able to form B because this was its ideal situation in which it was forming only 3 bonds. So now if this bond is formed, it will be forming 4 bonds. So to overcome that, this electron will be transferred like this, or it will be moved like that. So now what will we get? We'll get A single bond B and double bond C. And now A has an extra electron. A has extra pair of electron. So that's why there will be an negative charge on A. Same way, if there is B and on C there is a lone pair. So even then, so this lone pair and the negative charge, they will actually behave in the same way. So lone pair means again there is an extra electron. So I'll write it fast. It will be A single bond B double bond C, and on A then there will be a lone pair, right? And the transfer direction which we have to show, the movement will be the same as it was in the second case. Fourth case was for A double bond B and single bond C, and on C there was a free radical. Now here the transfer is of this single electron, the single electron, or not the pair of electron. So because it is single electron, so I'll have to use half arrow for this. To show this, I'll have to use half arrow. So this single electron moves from here to here. So that's why I show it using half arrow. Same way, out of these 2 pi electrons, which is shared between A and B, only 1 electron will come here. So this 1 electron here and 1 electron from one electron from AB bond and 1 electron from C. So that will form a double bond here, and the 1 electron which is left here, that will again go to A. So ultimately what we'll have here is, on A there will be a free radical because just one unpaired electron is there, then B double bond C, right? Let's see the next case, that is A double bond B single bond C, and on C there is a double bond, say double bond with D. So if this is the case, now again it will be movement of pi electrons. So these are the centers of pi electron, which is here in this double bond and in this double bond. So this pi electron, the pair of pi bond electrons, will move between B and C, and this bond will break and it will come here. So now what will this give us? It will give us A single bond B, double bond C, and single bond D. But D will have extra electrons. So due to that, it will have a negative charge, and A will lose 2 electrons. So that's why it will have a positive charge. And same thing will happen if there is A double bond B, single bond C, and a triple bond D. So it is similar from here to here and from this double bond to this single bond. So what we'll get is A single bond B, double bond C, and then C will have only double bond with D. And again, because D has taken a lone pair, so negative charge, A has lost the bonded pair of electrons, so that's why plus on A, right? Let's see the next, that is when we have A and a lone pair on A and B, and on B there is a positive charge. So now what will happen, again from the area of, from the site of high electron density, that is which we can see here, that A has a lone pair. So that lone pair will be given to this bond, or will be moved to this pi bonded or bonds. So now again what will happen here, you will have A will lose that, so A will have the positive charge, and there will be a double bond between A and B, right? And there is no lone pair on B, so that we have to make sure. Next, A negative charge on A and single bond B, positive charge on B. Exactly same thing will happen here as well, because lone pair and negative charge is almost same. So what we'll get here, we'll get A double bond with B, right? And it is an extra negative charge which has been lost. So again, a loss of negative charge is nothing but coming to neutral. So that's why both are neutral here. A and B both are neutral. There is no charge on A and B. And similar thing will be seen in other cases where we have taken, instead of A double bond B, A triple bond B and single bond C, and then on C there will be a positive charge. So now again same thing will happen, which we have seen here in this case, that is first case. So this first and ninth are same or similar. What will happen here, this triple bond, the here from double bond it was going to this positive side, so from here also the same thing will happen. And here it changed from double bond to single bond, here it will change from triple bond to double bond. right? And because AB from A and B, A has lost the pi electrons, so A will gain the positive charge, right? So like that, we can write for others as well. Let us complete itself. So 10th one is A, triple bond B, single bond C, and a negative charge on that. So now it will move from negative charge to the single bond. So it will, the direction of flow will be like this. So what we will get now, A double bond B double bond C, and there will be a negative charge on A, right? Next, 11th, A triple bond B, single bond C, and a lone pair on that. Same thing. So this second and 10th are same. Same way, this third and 11th will also be same. What will happen here? This lone pair will come here, and this will come here. So ultimately you will get A double bond B double bond C and a lone pair on A. And because C has lost its lone pair, you can also write it as like the positive charge on C and negative charge on A, or you can write it like this. Both are valid. Next, suppose we have A triple bond B single bond C, and this case here in this fifth and sixth case, right? So then let there be a triple bond D. So now again this and this. If you want to connect these, we are talking about this. These two are same. Okay, so A triple bond B, C, and C triple bond D. So now what we will get, there will be A double bond B, double bond C, and double bond D. D has gained an extra electron, I mean pair, so negative charge. A has lost it, so positive charge. Next, the free radical case, which we have lost here, I mean missed here, right? Fourth. A triple bond B, single bond C, and a lone pair on, not lone pair, a free radical at C. So again, only half of this electron, only one, half, not half, one electron. From here also one electron. And one electron from this bond, if that breaks, that will come to this. So what we will have, A double bond B double bond C, correct? And because A has gained one free electron, I mean unpaired electron, so even that has to be shown. These are the only directions of flow of electrons, right? Now let's move on to drawing resonating structures, and there are few points which we have to note or which we have to take care in order to draw resonating structures. So let's do that now, that is drawing resonating structures. So few points which we have to take care. General cases we have already seen, and now these we are going to learn how to draw the resonating structures. Resonating structures are also called canonical structures. And why we should know to draw these resonating structures is because if we are able to write it, it helps us find exact position of electron density in pi bonded compounds, like where on what all sites will be of pi electrons. So when we know that, then we can easily find the major product of any chemical reaction, which is obviously our ultimate goal, right? So let's go through these points one by one. First is the resonating structure differs only in placement of their pi electrons or non-bonding electrons, right? Though the structures, the resonating structures which we see, the only difference in them will be the difference in placement of their pi electrons or the electrons which are non-bonded electrons. So the bonded electrons or the sigma bond skeleton remains same in all resonating structures. That should not change. And that's what we have already seen above in all these structures which we have formed due to the transformation, due to the delocalization of pi electron. So we should make a picture in our mind that it is only the pi electrons which are moving, not exactly moving, but which we are showing in our diagrams as moving. So they are only the pi electrons. Nothing else will move. And where are the pi electrons found? Pi electrons are found in pi orbitals or p orbitals. Not all p orbitals are pi orbitals. Those orbitals which are perpendicular to the plane, they are pi orbitals. Right? So that is the first point. So these resonating structures differ only in placement or position of their pi electrons. In position of pi electrons or non-bonded electrons, nothing else. For example, say we have this, and there is a double bond here and a double bond here. So first we should see whether it'll be in that category or not, that general case of one of the general cases of resonance or not. So we have this A, double bond B, and then single bond C, and on C there is again a double bond, and then there is a D. So yes, it is a candidate for resonance. So which case is this? This is A, double bond B, single bond C, and on C there is a D. So how this electron transfer or electron movement is shown here, it is like this. So we'll show that, and we'll see that either these are only these pi electrons which are moving, right? So this pi electron will move from here to here. I mean, this bond will be formed. This pi electron will come here, right? And there is another pi electron that will actually come here. So from C it will go to D. So the next structure which we will get, that will be now here only single bond, then here a double bond, and here also a single bond. So here we'll get this, in the mid we'll get a double bond, right? And what happened here, this atom, this A has lost the bonded electron pair, so A will have a positive charge, and D, which is the last one, that has gained an extra pair of electron, so there will be a negative charge on this. So this is how the two structures will look like. As you can see, the main chain or the sigma chain is as it is. The sigma skeleton is as it is. That has not changed, right? So that is the first point which we should not forget. Second, the position of each atom in all resonating structures must be same. So that is actually first and second we can combine together. So position of atoms don't change. So I'm not drawing, you can actually use the same structure to explain this as well. Okay, so these are the 2 points. Next, all the resonating structures must be a proper Lewis structure. That is, the octet rule should not be violated, right? So proper Lewis dot structures. And when I write what are proper Lewis dot structures, these resonating structures. So we are talking about these resonating structures. So I'm not writing that again and again. What does that mean? It cannot expand their octet in any of the resonating structures. Or I'll say that cannot octet rule. Octet rule says outermost will have only 8 electrons. And that is applicable only for the second period. That is for carbon, nitrogen, oxygen, and fluorine. As we go down the group, so we know that there is no octet rule. Then there are 18 electrons in the outermost and 32 electrons in the outermost cell. So this is only for this. And we in our this organic chemistry, these are the only things which we have to deal with. So obviously we can just write cannot violate or must not violate the octet rule. All the structures have to follow that, right? So for example, if I write something like this, CH2 double bond CH NH3 and a positive charge on N. So this particular structure follow the conditions of what? A, if we see the case which is follows, that is A double bond B, and on C there is a positive charge. So it is one of the general cases of the resonance. But resonance is not possible here because after resonance, what will happen? How will you show that charge movement here? That from here, the electron has come to this place, right? So here I'll show it like this. That is, it is moving from this double bond to this single bond. So due to that, what will be the next resonating structure if this is the case? It will be CH2 single bond CH double bond NH3. Now what does that mean? That nitrogen is forming 5 bonds. And when nitrogen is forming 5 bonds, that means in the last orbit or in the outermost orbit of nitrogen, there are 10 electrons, right? So this means suppose if I write it like this, so I have written it, but this is wrong. Why this is wrong? Because this second structure is wrong. Why it is wrong? Because now nitrogen's octet is violated. It has 10 electrons in the outermost shell. Octet means actually 8. So there are several other examples also which we have to see. So you just not, you just, I mean, before jumping on to writing these resonating structures, you have to take care of this point as well, right? So other examples are, similar examples are that if in place of, just in place of N there is O, so it can be CH2 double bond CH OH 2, and on O there is a positive charge. Suppose if this is the case, again here, if you will form a double bond with O, that means O will be forming 4 bonds. Right? Not possible. Then what is the next one? Next one more example can be, I mean, we have taken NO, let's take F as well. So CH2 double bond CH, and instead of O, we can have FH with a positive sign. Again, one more bond with F is not possible. So all these cases are the cases which violate the Lewis dot structure. So that is not possible. So these are the 3 points. Next point. So what is the next point? Next, all the resonating structures must have same number of paired electrons and same number of unpaired electrons if they have any free radicals. So basically the number of paired electrons in both the structures should be same number of paired electrons. The pi electrons should be same, number of positive charge and negative charge should be same, or the total of positive and negative charge should be same. Or we can say the charge and the electron on both the sides should be balanced. So what is this 4th point? The resonating structures must have same number of paired electrons. That is, if they have pi bonds or positive charge, that means there is loss of 2 electrons, or negative charge, or if they have a unpaired electron, or say, sorry, lone pair as well. So these are all paired. So same number of paired and same number of unpaired electrons, and same number of unpaired electron. And we know what is the case of unpaired electron if they have a free radical site, right? So this should not be violated again. And this we have seen everywhere in the examples which we have seen above to study these transformations. So you take any example, for example, take this 3rd one. So there is a lone pair here. There is a single lone pair on C. And same is here, single lone pair on A. How many pi electrons are there? So there are only 2 pi electrons here. I mean pi bonded electrons. That is this double bond. Same way here also there are only 2 pi bond electrons. But here the position has changed from A between A and B to B between B and C. That is the only difference. Now see the 12th one. If you see the total charge, none of them have any charge, right? And number of pi electrons, 2 plus 2, 4, and 2 plus 2, 4. So there are total 8 pi electrons. And see here in this 2 pi electrons, 2 pi electrons, 2 pi electrons, total 6, and plus these two are also pi electrons. So total 8 pi electrons, right? So in this case, you have 8 pi electrons. Here also you have 8 pi electrons. This is neutral, that is charge is neutral. Here also you have neutral because the molecule is neutral. There is a site of positive charge and negative charge, but that is what delocalization means, that these charges or electrons are not located or fixed to a single location. They are capable to dislocate or relocate to some other sites. Clear? So that's what we mean when we say the total charge on both the side, on all the resonating structures should be same, the same number of paired electrons and same number of unpaired electrons. Even unpaired electron, the free radical thing, which if we want to see, even there we can see here, right? There is a free electron, just one free electron here, and here also there is just one, not free electron, sorry, free radical, right? There is one pi bond, there is one pi bond here. Number of pi bonds, even if they change, but number of pi electrons will not change. That's what we have seen in example 12. So that was the fourth point. I have not written the example here because examples we have already seen up. Next is fifth point. That is, if any conjugate position has more than one pi bonds, then only one pi bond take part in conjugation. So I'll just write if multiple pi bonds are there at one site, then only one pi electron or one pi bond which has two pi electrons. So only one pi bond takes part in conjugation. Conjugation is this alternate arrangement of double bonds, or you can say delocalization. So what does it mean? Suppose you have like this. So there are two pi electrons, two pi bonds there, but only one pi bond takes part in the conjugation. So what will happen now? From here, bonded pi electron will come here, and that's why this will lose its electron to the next carbon. So what we will get is sorry. A negative charge here and a positive charge on this carbon. So only one pi bond is used, or only one pi bonded electrons, that is two electrons in one pi bond, only they are used for delocalization, or this delocalization is also called conjugation. Right? Next is that if any conjugate position has pi bond along with positive charge, negative charge, odd electron, or lone pair of electron, then only pi bond takes part in conjugation. that we have already seen that if there is a pi bond here, right, and there is a positive charge or negative charge on this, then this pi bond, only the pi bond will take part in the resonance or conjugation. Not then, for example, if there is a positive charge here, then positive charge means there is no electron. So that is not our concern. But if it is like this, that there is a negative charge here. So in this case, what will happen? And suppose if there is a double bond here as well. So A, double bond B, C, and on C there is this negative charge. The negative charge is not on C. Negative charge is on double bond, which is part of double bond, which is connected to C, right? So here again, it's not the negative charge which will take part in the, this will remain as it is. This won't delocalize. It is only the pi bonded electrons which will localize. So this will come from here to here and this will come here. I think it is clear that in conjugate positions has pi bond, if, which we can see there, if conjugate positions have pi bond, then in that case, pi bonds with positive, negative, or lone pair or free radical, then only pi bonds conjugate. This is the example. Okay, so we'll continue with this session itself, and I'll restart this as soon as this session ends, because just 1 minute is left, and we'll continue with the same organic chemistry sessions itself for today, because I want to finish this electronic